Okay, so once again, I'll welcome you back to my YouTube channel. It's Hyper. You can subscribe, you like, and you share the link with your colleague so that they also benefit from the same cause. We are going to look at a derivative of benzene called methylbenzene. That is the IPAC name. Actually, methylbenzene is one word. So this gap, when you're writing, please don't leave this gap. Write it as one word. Basically, we write it as methylbenzene. So it's one word, methylbenzene, and traditionally, it was known as taurine, which still holds, but the IPAC name is methylbenzene. Methylbenzene has got molecular formula. Since we add a C, now for benzene we have 6 carbons, but for methylbenzene there will be 7 carbons, and then we shall have 8 hydrogens. Why? Because here the CH3 substitutes some hydrogen, so implying that for the case of benzene, for the phenyl group, we have a phenyl group that is C6H5, but then you add another carbon for this and then 3 hydrogens, so making it C7 and H8. So in other words, it's a methyl group attached to the phenyl part of the ring. So basically, for the case of methylbenzene, we shan't talk about it too much, but I'll first highlight on the aspect of melting point of methylbenzene. I'm going to make a comparison between the melting point of methylbenzene and benzene itself. Then after that, we are going to look at methods of obtaining benzene. Then from there, we are going to look at inductive orientation on the benzene ring, basically with respect to the methyl group. Then we shall also look at other substitutions that can happen on the benzene ring, and that will take us to the chemical properties. That work I've just talked about is somehow very brief because the details of the reactions show us the orientation of different reactions or of different substituents that are attached to the benzene, rather to the methylbenzene. Well, we are going to compare the the melting points of methylbenzene and and basically benzene. So, this is so common, especially in organic analysis. There are those questions of explanation of observations. They can ask you, maybe can say methylbenzene has a higher melting point than benzene. Methylbenzene has a higher melting point than benzene. Then I can say explain. Explain. So this question can take something like 4 marks, depending on the guide and the marking points that are being generated by an examiner. But basically, when we talk about methylbenzene having a higher melting point than benzene, we are going to see that in both methylbenzene and benzene itself, we are going to see that the molecules are held together by weak van der Waals forces of attraction. But the strength of the weak van der Waals forces of attraction increases with an increase in the molecular weight of that very compound. So basically, in both benzene and methylbenzene, the molecules are held together by weak van der Waals forces of attraction, but the strength in the weak van der Waals force of attraction varies depending on the compound you are talking about. So one, we shall talk about the fact that in both benzene and methyl benzene, in both benzene and methylbenzene, we are going to find out that the molecules are held together by weak van, we have to begin with capital V, der Waals forces of attraction whose strength increases with the molecular mass. Now, from molecular formula, you can easily calculate the molecular mass because for methylbenzene, it is C7H8, while for benzene, it is C6H6. So on comparison, ideally, you can see that the molecular mass of methylbenzene is higher than that of benzene itself. Now, since methylbenzene has a higher molecular mass, than benzene, we are going to find out that its molecules, the molecules in methylbenzene, its molecules are held by stronger van der Waals forces, by stronger van der Waals forces, than that of is held by stronger van der Waals forces than that of benzene, or than benzene, that require, of course, since they are a bit stronger, they will require a higher amount of energy, to break. Okay, to break. So this question, let's review the question, members. The question has been, the question is wrongly set according to the real chemistry, according to the chemistry. It is methylbenzene has a lower melting point. We are going to see the however part. Why is it that it has stronger force of attraction that would be hard to break, but it has a lower melting point than benzene? So check. It must have a lower melting point than benzene. So we are going to bring in the however part, because literally, or by chemistry, we are going to find out that the melting point of benzene is higher than that of methylbenzene because of what we are going to see. So much as the stronger forces, much as there are stronger van der Waals forces of attraction in methylbenzene than in benzene, but we are going to find that, however, we're going to find that the melting point, I'm using MPT for the melting point. However, the melting point of benzene is higher than that of methylbenzene, because now that is where we're going to pick from. Because I'm taking it to another page. Let's see the reason as to why the melting point of benzene is however higher than the one of methylbenzene. So the reason behind that, we look at the arrangement or the planar structures of these two. We look at the differences in the structures of these two. And when your chemistry advances, you're going to look at the detail of this. So we are going to see that because the planar symmetrical benzene, the planar symmetrical benzene can pack closely together, together in the crystal, hence having stronger cohesive forces, than methylbenzene, molecules in which the methyl group makes the methylbenzene molecules not to have such close packing. So when you're describing, you have to start from the first one. Basically, we've seen that the melting point will always depend on the forces of attraction holding these molecules together. So we've seen that in both benzene and methylbenzene, the forces of attraction holding these molecules are very weak. But the strength of these weak van der Waals forces holding the molecules increase with the molecular weight, implying that in methylbenzene having the higher molecular weight, it would be hard to break. The molecules would be hard to break compared to benzene, since they would have stronger forces of attraction. However, the melting point of benzene stands out to be the highest compared to the one of methylbenzene, simply because benzene takes on the planar symmetrical shape, and the particles or the molecules can pack closely together in the crystal, hence having stronger cohesive forces. So we shall find that from one molecule to another, the forces, the cohesive forces are stronger as a result of the close packing, which is a result of the planar symmetrical arrangement of the molecules of benzene. However, when you come to methylbenzene, the molecules in which the methyl group are present, this methyl group makes methylbenzene molecules not to have such close packing, meaning that the close packing is absent in methylbenzene, but it is present in benzene itself. So that is the reason as to why you have this kind of difference. So that is it for the case of this. Now, we are going to look at methods of preparation of methylbenzene. You can always revisit this work so that you master it from the first dot. So we are going to look at methods of preparing methylbenzene or preparation of methylbenzene. So preparation of methylbenzene. One, we are going to have from benzene itself. We looked at this yesterday in the reactions. So you can get it from benzene. Then for this case, what happens in benzene? So methylbenzene is formed by basically bubbling chloromethane through dry benzene in presence of anhydrous aluminum chloride catalyst at a temperature of 40. Even if you carry out the reaction at room temperature without showing the temperature, it is very okay. So we bubble chloromethane, basically. We bubble chloromethane, so through benzene. So by bubbling chloromethane through benzene, shall have CH3, Cl, and you do this in presence of aluminum chloride. Of course, the result will be chlorobenzene. Sorry, methylbenzene. So you can carry out the mechanism here. As we saw yesterday, we said that basically the halogen carrier will first react. So we shall have CH3. We need to first bring out an electrophile. So we shall have this, and then shall have the aluminum chloride. So you'll form CH3, which is our electrophile, CH3 plus, and then aluminum chloride intermediate. But basically this one here, even we can accept the partial arrows. Anything you put is okay. So then now you have benzene, and then your electrophile CH3 with a plus. So the methyl group will momentarily attach itself on the benzene ring, and where the bond has left, we shall have a positive charge. There will be CH3. Then the hydrogen which is to be replaced will stabilize the ring, and it leaves. So that way we shall be left with benzene ring, or with methylbenzene, sorry. So be left with methylbenzene. That is the first method. The second method is from bromobenzene, and that is what you call the Fittings reaction. That is from bromobenzene. That is the first method. I guess this is very, very okay because the second video shows how we were coming up to this extent. So now we are going to look at from bromobenzene. And we say that from bromobenzene, one can call it the Fittig's reaction. Now, from Fittig's reaction, that is where we have methylbenzene being formed from bromobenzene. Basically, you have your bromobenzene, and you can tell the source of bromobenzene. We can get bromobenzene by halogenation, whereby we get benzene, you treat it with bromine in presence of a halogen carrier. So now, when we add sodium silyl to a solution of benzene in iodomethane and dry ether or chloromethane and dry ether, you'll be getting your answer. So basically, if you have CH3, Cl in sodium and dry ether, this will be able to give you the product, which is methylbenzene. Now, we also have what we call the industrial scale, the industrial preparation. Yeah, we've got the industrial preparation. And for you to prepare methylbenzene on an industrial scale, basically, on industrial scale or industrially, you may not use this in synthesis, but it is worth being known. So on an industrial scale, we get methyl cyclohexane. We basically treat methyl cyclohexane, CH3, that is methyl cyclohexane. When you treat methyl cyclohexane with a compound, okay, it is an inorganic mixture of catalysts, and the first catalyst is called molybdenum 3 oxide. We have molybdenum 3 oxide. You treat it with the aluminum oxide. This is a mixture of catalysts. I've said that this is called molybdenum 3 oxide with aluminum oxide at a temperature of 560 degrees Celsius and high pressure. This will be giving you directly methylbenzene. So these are the only 3 methods that maybe one can rely on to produce what we call methylbenzene. Still, in my same video, I'm going to take you through the orientation. I'm going to take you through the orientation. The inductive orientation in benzene ring in relation to the methyl group. So basically, we are going to see the different products that we form as a result of different substituents that we add. So I will first summarize it for you. And then I write the equations at once. Yeah. So basically, we are going to have those other subunit, inductive orientation. On benzene ring in relation to the methyl group. So here it is somehow tricky, but very easy. Now we are going to find out that just like benzene, because the moment we look at the inductive orientation didn't mean that we are nearing the chemical properties. Now, just like benzene, Methylbenzene also undergoes electrophilic aromatic substitution reactions. Yeah, so it can undergo sulfonation, it can undergo alkylation, it can undergo acylation, it can undergo whatever, it can undergo those reactions that benzene undergoes. Now, I want you to note that if, for example, I'm going to use an example of sulfonation. If, for example, I carry out sulfonation of methylbenzene using concentrated sulfuric acid, okay? So if you use conc sulfuric acid, now for the case of methylbenzene, we are going to find out that we form a mixture of different products. So we shall form a mixture of products, or what we call the isomeric. We shall form different isomers, but in the same reaction. So when you carry out sulfonation of methylbenzene, you're going to form a mixture of products, and one of them, we shall have CH3 here. One of them is SO3H. We are going to see how to name these. Another one will be SO3, sorry, CH3. We have SO3H on this position. Another one will be, we shall have SO3 on this position. Then here we shall have CH3. So you've seen that we form a mixture of different products. Actually, for sulfonation, this one we form 32% of this product. Here we form 6% of this product, while here we form 62% of this product. What does it mean? These isomeric products, provided the substituent is on the second carbon, when you're from this side, this is the first carbon, this is my second carbon. These, the isomeric products can be named using ortho. For this case, we shall use ortho. On this second position, we call it ortho. Then on this third position, we call it meta. Then the fourth position, we call it para. They begin with small letters, these prefixes. Now, one also can call this one O, one can call this one small m, one can call this one small p, for purposes of naming. So now, each prefix matches with numbers 2. So as well, you can use 2, here you can use 3, while here you can use 4. So depending on where the substituent is attached, it gives you how to name it with. For example, for this first isomer, which is a 2 substituted isomer, one can name it as ortho-methyl benzene sulfonic acid. One can name it as ortho-methyl benzene sulfonic acid, ortho-methyl benzene sulfonic methylbenzene sulfonic acid. This one here, on the third position, one can name it as meta, then hyphen, methylbenzene sulfonic acid. Then the one on the fourth position, one can name it as para, hyphen, methylbenzene sulfonic acid. Instead of using these, one can as well say O, methylbenzene sulfonic acid. One can say M, methylbenzene sulfonic acid. One can say P, methylbenzene sulfonic acid. So that way you would have named it. Now, from the equations shown above, you can see that the ortho, which is 32%, and the para isomers, which is 62%, are the isomers that are formed in larger amounts than the meta isomer, implying that these would be the 2 main products if you're writing this equation. So we are going to find out that in the reactions with methylbenzene, we shall be forming a mixture of isomers. It may not give you the one substance. So similarly, the way this one has happened is the same way other reactions will happen. Actually, for nitration, Friedel-Crafts alkylation, acylation, and halogenation, we are going to find out that we shall be forming an ortho product and a para product. What am I trying to mean? I'm trying to simplify to you that when we go to the reactions, we shall be looking at the fact that sulfonation, nitration, alkylation, acylation, and halogenation, the mechanisms won't be different as we shall be seeing, but we shall see that all those reactions that I've talked about, they yield an ortho-para product. So for example, once more, if you get, for the case of nitration, if you have methyl benzene, CH3, and you treat it with the conch nitric acid, conch sulfuric acid at 55 degrees Celsius, you're going to form a product on the second position. The nitro group will be on the second position, and here you have CH3, then plus, you will form a product on the para position, that is NO2 here, and then CH3. Naming these, one can name this as 2-nitromethylbenzene, nitromethylbenzene, or one can, because this is the ortho, one can say or nitromethylbenzene. This one can call it 4. This one where we have 4 here. So one can call it 4-nitrophenylbenzene, or one can call it para-nitrophenylbenzene. So you can name them that way. The same applies to when one has carried out acylation. For the case of acylation, they're not different from those of benzene, only that we form a mixture of products. So if you have methylbenzene and you add the CH3, COCl in presence of maybe iron 3 chloride, you'll be forming a mixture of products. You'll be forming CH3 here. You'll be forming COCH3 plus you form another product, CH3 here, then COCH3. The same applies when you're carrying out halogenation. For the case of halogenation, you'll be having your methylbenzene and you're carrying out halogenation. Maybe, for example, you're treating it with chlorine in presence of aluminum chloride, and it will yield a 2-substituted product, CH3, then Cl plus a 4-substituted product. So a 4-substituted, here you have CH3, and here you have Cl. The same applies when you're doing alkylation. When you're doing alkylation, you have your benzene, your methylbenzene, CH3. You carry out alkylation. Maybe you're adding chloroethane, CH3, CH2Cl, in presence of maybe aluminum chloride. You'll be forming a mixture of 2 substitute product. You have CH3 here, and here you have CH2, CH3, plus you form a 4-substituted product, which we shall have as which is on the 4th carbon, CH2, CH3, then here we have CH3. So all these are 4 different reactions in addition to the sulfonation, but you find out that we form the ortho product and the para product. We form a 2-substituted and a 4-substituted product. So all the reactions above imply that the methyl group is ortho-para directing, or it is a 2,4 directing group. The moment you're having a methyl group, and it is reacting with these, if it is a methyl benzene that's reacting with all these substances we've seen, the product you form will be an ortho-para directing product. Now, I want you to know the reason as to why methyl benzene is more reactive, far reactive than benzene. Why is methyl benzene more reactive than benzene? The reason is simple, because now I want you to compare benzene and methyl benzene. This is methyl benzene. We are comparing it with benzene. Remember, for the reaction to take place in these compounds with the bonds, those compounds in which we have high electron density, that is where, meaning there is much source of electrons, and therefore the reaction is quite much clear. So now, for the case of methyl benzene, this methyl group donates electrons to the benzene ring, increasing its electron density and thus the attack by the electrophiles, compared to the benzene, whose electron density is lower because it has no donating group. So in a case where you have a donating group like a methyl group, which donates electrons to the benzene ring, we shall find out that the benzene is now rich in electrons. So the reason here is simple. You'll just say because the methyl group donates electrons towards the benzene ring, hence increasing its electron density, making it more reactive towards the electron deficient species, or what we call the electrophiles. Okay, let me highlight it for you. You'd say methyl benzene is more reactive than benzene because the methyl group donates electrons towards the benzene ring, hence increasing its electron density, making it more reactive, towards the electron deficient species. Towards the electron deficient species or electrophiles. So basically, that is what we'll talk about. Now, we are going to see that since the methyl group is an activating group, being an activating group is the reason as to why it forms the ortho-para substrate group, because it is activating. Actually, those groups which donate electrons to the benzene ring, making it more electron efficient, are the ones that we call activating groups. However, we have those ones which we call the deactivating groups. Because remember, I'm telling you about the orientation group with respect to the methyl. Orientation of the groups around the benzene ring. For example, now, I want you to compare with this. If at all you're carrying out the same sulfonation, but instead of using the methyl group, we use nitro group now. Remember, with the methyl group, the products were directed to ortho and para. But this one now, it is going to be the same reaction. I'm going to carry out with fuming sulfuric acid. at a temperature of 35 to 50. But we are going to find out that because of the substituent attached, now this is a deactivating nitrobenzene. This nitro group is deactivating. Instead of giving electrons to benzene ring, it removes electrons to benzene ring, making it deactivating. So for the case of a deactivating group, the ortho and para products are not formed. Instead, we form a meta product as the major. So for this case with a nitro group, we form small percentages. We form minimal amounts of these products. Of course, we shall have the ortho still, but I'm going to show you the differences in the products. Plus NO2, SO3H, plus NO2, SO3H. The difference is that here we form 6.4%. I want you to see. Here you form 93.3% of the meta product, but here you form 0.3% of the para product. What does it mean? It means that for those deactivating groups, those groups which tend to withdraw electrons from the benzene rings, make it less electron efficient, those groups, what they do, they make the product appear on the meta. So for the withdrawing groups, I want you to note this, that for the withdrawing groups, the main product is on the meta. I'm going to give you a summary of the withdrawing groups. So the withdrawing groups, they form the products on the meta position, while the donating groups, the electron donating groups, they form a product on the ortho and the para positions. Okay, so it means that the nitro group is a meta directing group, while the methyl group was an ortho para directing. I guess I'm clear. Now here we are going to find out that in comparison to the reactivities, the nitrobenzene is far less reactive than the methylbenzene. It's far reactive than the methylbenzene because the nitrobenzene instead withdraws electrons from benzene ring, reducing its electron density, making it less reactive towards the electrophiles, while the methylbenzene donates electrons towards the benzene ring, making it more, increasing the electron density of the ring, making it more susceptible to attack by the electrophiles. Now, I've told you, I want you to remember that a group that makes a benzene ring more reactive than benzene is the activating group, meaning a methyl group is an activating group, while a nitro group is a deactivating group. Okay? And I've told you that activating groups are ortho, these ones are ortho and para directing, while the deactivating groups are meta directing. I guess that is clear. However, I want you to note this, that however the halogens withdraw electrons from the ring, for them we take them to be orthopara. So the only distinction or the only exception that you bring here to be orthopara directing, much as they withdraw electrons from the benzene ring, are for the halogens. For the case of halogens, much as they are deactivating, these ones are deactivating, but they are, much as they are deactivating, they are also para directing. We are going to see now at our level within our scope. We are not supposed to be looking at those further reasons, but I will arrange a video and I give you a blast on this. So we see the reason as to why the halogens are deactivating, but why do they form orthopara directing groups? Some compounds which are deactivating and form orthopara groups, you find out that the lone pairs of electrons of those of those substances tend to give electrons to the benzene ring, ending up activating it. So I'm going to summarize for you a few of the orthopara directing groups and the meta directing groups, and we call it an end of this session. So the orthopara directing groups, ortho, you call it ortho, and para directing groups. And here we shall have the meta directing groups. The meta directing groups, they direct to 3 position, to the 3rd position, while the orthopara, they direct to the 2 and 4th positions. These ones include NH2. They also include OH. Actually, most of them with lone pairs of electrons are orthopara directing. OCH3, one can have OR because it can be any alkyl. Then we can have NHR. We have NR2. We have CH2CH3. We have CH3. These ones are activating. These ones activate the benzene ring by donating electrons toward it. But much as the halogens, the fluorine, the chlorine atom, the bromine atom, the iodine atom, much as these are deactivating, as I told you before, they also form a 2 and 4 substituted isomer of benzene. Then for the case of the deactivating groups, I'll begin with the nitro group, which we have talked about. We shall have the cyanide, we shall have the carboxyl group, we shall have the sulfonate or the hydrogen sulfate, we shall have the aldehyde group, we shall have the ketone group, we shall have it can be as big as that. So these ones are deactivating, and since they are activating, they are meta-directing. I want you to note that for most of the groups which deactivate the ring, the atom directly attached to the benzene ring usually has a double bond attached to it. Those ones which are deactivating, we have said that the atom directly attached to the ring is always having a double bond attached to it. There is no big chemistry there. There is no big chemistry there. But what I'm trying to mean is that for these ones which are deactivating the ring, the atoms attached to them are always having a double bond attached to them. For example, this. But for now, let's have it at this. And we are going to look at the chemical properties of methylbenzene in my other video. I wish you all the best for now.